opportunity. So myself, Ganesh Kumar. Uh, so I'm currently the CTO, Chief Technology Officer for SuccessBridge, and I have close to 10 plus of years of experience in the semiconductor domain. Worked for top service-based MNCs and top one semiconductor company like Intel. So I would like to share my experiences and help in guiding the new graduates or upcoming engineers and help them understand the chip designing and semiconductors um, and provide awareness to everyone. So this is to everyone, for all the audience, and going forward. So this will be our agenda for today. I will be uh, discussing on the introduction to chip designing, latest trends in semiconductors, challenges and geopolitical issues that are affecting semiconductor industry. And we'll discuss on the career growth and future scope in semiconductors. And we'll also go through the journey towards Made in India. After that, we can have our discussions and question and answers open for questions at the time. Okay. So many of the graduates from electronic background or electrical background, for that sake, any engineering background. So this chip designing and manufacturing or a semiconductor process is not taught in their academics. So what is taught in the academics is only the basic fundamentals of electronics and electrical communications. So all these fundamentals are taught, which are very essential and helpful. And after academic, going into semiconductor or the core domain for this background people, it is very much essential that there is a skill gap that is very much required for entering into chip designing and semiconductors. So this particular session today, we will address all the parameters, introductions, and feature scopes and growth. So please pay attention. So this is a slide that you're seeing, a chip specification, design verification, RTL synthesis, and partitioning of chip, design for test, floor planning, placement, clock tree synthesis, routing, final verification, and GDS. So this is the basic cycle of a chip, starting from design abstraction to manufacturing. So this particular cycle is basically present in every industry. This is not just in semiconductor, any manufacturing industry. We will have a life cycle of designing a chip or designing a machine or designing a product. So this is the life cycle of designing a chip. So initially, the chip specification that you see is the initial stage where the product-based companies like fabless companies, Oppo, OnePlus, MI, LG, Samsung, if you take any electronics company out in the market, they have their own product. It's not necessary that they have their own fabrication unit. Okay, so there are fabless and fabrication companies. So fabless is where they have their own product, but do not have their own fabrication unit. So they are dependent on some fab like Intel, TSMC, Samsung. So the majority of the times, you will have less number of fabrication industry and fabrication companies compared to fabless companies, because anybody can come up with a product. Not necessarily he has its own manufacturing company. So the company, the fab gives you the services to design any product in this any chip. So the fabless companies like any mobile manufacturer company, Oppo, OnePlus, Samsung, any take any Android mobile phone or iOS mobile phone that you have in the market. So majority of the times, apart from Samsung and Apple, all others are fabless. So they are dependent on other companies in designing their own chip. Okay, so they come up with a chip specification and come to your client and ask them to design my chip. So when they come up with the chip specification, they'll say, okay, I need this much of clock frequency. I need certain parameters, certain functionalities to be added in this IC. So I need this IC to be adapted to the artificial intelligence or new functionalities that we have in the market currently. And the technology node, the fabrication technology, what kind of fabrication technology that need to be used. So all these come into chip specification. And going forward, once the chip specification is accepted on a multiple debates with the client, they will go with the RTL coding. So RTL engineer is required there. So first stage, design abstraction and RTL design engineer is the first engineer who will start writing the code for the said specification. So once the RTL designer writes a code in RTL languages like Verilog, VHDL. So majority of the times Verilog is pretty much used. So once he writes a code, then it has to be synthesized. The netlist has to be synthesized. The RTL has to be converted into gate level, where transistors and all are libraries are provided for that. So second stage will be design verification or the functional verification. So in chip specification only RTL design also comes, because you need a architect, chip architect, and RTL design engineer, senior RTL design engineer, to approve the chip specification. So going forward, the functional verification engineer will take up the verification process of validating that IC or the RTL code that has been written by the RTL engineer, whether we are able to get the expected output of the transistor behavior. So he will try to create a test case similar to the software engineers. In software, we have a software testing and software development. So software development is equal to the RTL design engineer, and the software testing is equal to the functional verification. So he will write a test case and verify the code is perfect or not. So as long as the syntax and the functionality is perfect, the verification passes. Need not be that internal behavior might not exactly match. If the syntax matches and expected output comes irrespective of the behavior, then functional verification will pass. So there is a catch here. We'll discuss going forward this backdrop of design verification, where we correct this and proceed to the next stage. So after that, RTL synthesis. So RTL synthesis can be done by the RTL design engineer or RTL synthesis engineers or a physical design engineer. So synthesis can be done by any person who has a synthesis tool. So chip designing industry is pretty much dependent on the EDA tools. So EDA tools like Cadence, Synopsys, Mentor. So there are other tools apart from these three vendors, of which help in post-manufacturing testing. Okay, so Cadence, Mentor, and Synopsys are the biggest EDA players in the market that we'll see. They help in providing all the customizable tools to this design service manufacturers or anybody who want to start a semiconductor company. He can just go and purchase the license from any of these EDA vendors, and he can do this chip designing. And he has to definitely have engineers hired. So we'll go into that later. So once the synthesis is done, then they divide the entire full chip into multiple partitions. So multiple partitions are divided, and next they go to design for test. So design for test is something where the functional verification backdrop is covered. So we do not verify the behavior, we just give input and check the output. So what happens internally, irrespective of the behavior of the logic, okay, so as is it functioning as required, or is there any stuckets or any shorts and opens, okay, that we will not be able to diagnose post manufacturing. So design for test plays a biggest role throughout the chip manufacturing and even after manufacturing also. So DFT plays a key role because it helps in adding the test logic into the design so that you can test each and every logical gate in the entire chip, even after post manufacturing. Something like you have a mobile phone or a laptop, it's heated up or it's shut down suddenly, and the display has gone, CPU is heating up, or RAM is heating up. Any peripheral issues or a display issues or any issues with the device, the chip or the motherboard, you go to technical person, the technician, and you give your device and tell him the issue that you are facing, and he will diagnose your device, and he will then provide a solution. Either something has gone wrong, a certain there are multiple ICs on the chip, so a single IC is not working properly due to its fault issue or any heated up issue. Many issues are there in the chip design which can cause the IC component to malfunction. So then he sends this to the chip manufacturer, the mobile manufacturer or the laptop manufacturer, and he then re-diagnoses and finds the root cause and then refurbishes the IC and gives back to the customer. So in order to do this 3 stages of diagnose, find the root cause and refurbish, you need DFT, test patterns. The final test patterns delivered by the DFT engineer. So DFT plays a crucial role. After parallel to DFT, this physical design is a designation in the chip designing. So floor planning, placement, clock tree synthesis, routing, final verification, including GDS, all part of physical design. So if you are a physical design engineer, you should be aware of all these parameters. Should be need not be an expertise in all these domains in the early days, but once he starts working in one project, he might work on floor planning. In another project, he might add on floor planning and clock tree synthesis and routing. So a basic engineer will execute all of these, but may not be an expertise in all of these domains. So this all comes into physical design. So the final stage before manufacturing, the physical design engineer plays a role in floor planning placement, clock tree synthesis, routing, and final verification. These are then the silicon level where they directly take the chip size based on the chip specification. What is the size? It's a mobile phone. What is the length and breadth, a height of this particular chip? What is the area for the display? Area required for RAM and other components within the IC, CPU, GPU. So all these components, they have to be properly floor planned, and placement stage will be taking care of this. After that, they process clock tree to, because clock is the basic element and control signal for any digital IC. So if there is no clock, there is no functionality. So you need a clock for any digital IC to work. So clock tree synthesis across the chip will happen by the clock tree synthesis engineers, CTS engineers. So followed by routing. So once everything is planned, then they try to perfectly establish the connections. So routing is a biggest and crucial stage played in the floor plan, played in the physical design environment. After that, they have to verify what they have done so far, and then it goes to manufacturing. Okay, so I just given the basic information of each individual engineer played in the process of chip designing. So going forward, we'll get to know more about chip designing and semiconductors. So this is what you see here is a combination of product design, front end, wafer fabrication, and the back end until final test. So end-to-end process, what you can see here is a detailed explanation where you can see an IC has been designed. So IC design team, like RTL design team, will work on this IC design. So IC design might work, contribute all these life cycle parameters where RTL design, design verification, DFT physical design, and sign off to AT. Each one is a designation contribute to designing IC. And once IC has been designed, parallelly, you come up with a wafer, because this is a silicon wafer that you'll see. Wafer is a base on top of which your IC gets manufactured. So wafer is very much required. So what type of wafer you are using? A silicon wafer or a gallium nitride wafer? So we have three types of technologies that for in today's era of 2023, we have come up to gallium nitride, starting from silicon to silicon carbide and moving on to gallium nitride that we will learn going forward. Okay, so silicon is basically extracted from the sand, and a purified silicon after going with multiple stages of process that will go, I will see what happens. So, and once silicon ingots are created in the molds, and you extract the wafer by slicing it down into thin layer of silicon wafer. So after that, once the wafer comes, you perform all this process to create a proper wafer. So oxidation, lithography, etching, strip and cleaning, ion implantation, chemical vapor deposition, metal deposition, chemical and mechanical planarization. So these all stages have to be, the wafer has to go through all of these stages to get a fine-tuned wafer. Once you have a wafer, you check the wafer by doing probe test, and you verify that all the corners of the silicon wafer are working as per the requirement. Then they go with the assembly and final testing. So we'll see what is the in-depth of wafer to packaging. So wafer and packaging plays a crucial role in manufacturing process, because without wafer you cannot create an IC, a physical IC, and end of the IC comes up with a proper packaging, okay, with the pins, physical pins. So there is a process involved in all of these stages. So what we call here is a wafer maker and a semiconductor maker, with a wafer manufacturing process, wafer fabrication front-end process, assembly and packaging, and giving out NIC. So a silicon ingot will be sliced down and grinded, multiple steps of grinding, okay, multiple steps of grinding AN, and polishing and cutting them into each individual die. So this particular silicon wafer is having multiple dies. Okay, so cutting is where they are not separated. They are just IC is not at all not cut physically, but the dies are separated so that your mobile phone IC or any IC that you wanted to design, that design will be tested on each individual die. So how many dies you have per a wafer, based on the size of the wafer, you can have that many ICs coming out of a single wafer, like this. Okay, so once it is done and cut, you get a neat packaged IC. And we'll see the technology trends that we have in the process of coming to this current stage of semiconductors, starting from 2018 to 2036. We have a roadmap with each technology node. And this basically what we have taken is from the sources is from Intel. So this is the technologies provided by the Intel, starting from N7 to going forward. Designing is happening, R&D is happening to get A2. A2 is where it is 1.2 nanometer. So it's basically 1 nanometer. Starting from 18, everything is 1 nanometer. So in 2018, we had 40 nanometer. We used FinFET. Till 22 nanometer, we have used FinFET. And 21, we started using gallium arsenide. And all the stages till 1.6, we are still using GAA. And going forward, Intel is going to use CFET, so which is an advanced technology. So all these technologies will contribute to reduce the size of the transistor, where the transistor bandwidth is 1.6 nanometer or 1.8 nanometer, very less. Okay. So these are the current trends that we have across the market, the semiconductor market. So what you can see here is a market of the semiconductor globally across Asia Pacific, Japan, Europe, and United States. So the market is where your more consumers are present, where more selling and buying is happening. So Asia Pacific stands high with a high market compared to Europe, Japan, and United States. So this is the latest statistics taken from the World Semiconductor Trade Statistics, WSTS. So this is very much latest. And what you see in the billion USD is the total market for the semiconductor across the world. So Asia Pacific, India also comes under Asia Pacific. And what we see today with the current innovations is IoT, the latest trends in IoT, artificial intelligence, and their advanced technologies in artificial intelligence, advanced materials. Material is something like silicon or a silicon carbide or a gallium carbide. So what is the or a gallium nitride? So any of this material that you're using, which gives you better performance in the usage of high power, low power, medium power usage, because market is so wide that you need an IC starting with a basic motor car to the full sports car, and you have many electronic appliances which require and which has a wide variety and differentiation of power consumption and frequency usage. So the materials are very much important and play a very crucial role in semiconductor, because without the material you cannot advance further. So there are certain companies like Custom Dot, EP Innovatech, which is doing innovations in advanced materials. And coming to novel architectures, there are certain companies that you see. These are the current trends of 2023. What you see, these are the companies that are portrayed on the left and right side of each technology. So they have their own intellectual properties and patents created on the innovations that we are using today. So advanced packaging, which is very much required once IC is designed, and 5G technology. Falcom is very much efficient in designing 5G mobiles, 5G technology, the modem. So in-house chip design, there are many companies. So the recent trends are Semi 5. It has created a vast differences in producing high-end in-house chip designs. In-house chip design is something chip is designed and manufactured within their own company. Fabrication technologies. Again, fabrication technologies also play similar role of advanced materials. So certain companies who are expertise and working on fabrication technologies like EHVA and Unisys, they contribute in innovations, creating new innovations on the existing technologies. And automotive chips, Renesas, Lidwave, there are many other companies that are contributing with the automotive chips, designing and manufacturing. And there are few companies, they are not competing with the market, but they have their own sustainable manufacturing process of a fixed products. So they have a very standard and sustained flow of manufacturing their own ICs. So Digito is one of the company. So these are the current trends to date. So what we have. So going in depth little bit of the major aspects of latest trends is advanced material, because this is the initial thing or a element that helps in designing any kind of an IC. So if you don't have this basic semiconductor material, you cannot design any IC. So let's go little bit into advanced materials and what are the technologies, advanced technologies that currently we are going through, and what are the companies that are contributing in bringing up new innovations into this technology. So what we have is a silicon followed by silicon carbide and gallium nitride. So GaN. So these shortcuts that you see anywhere while purchasing any electronic device. So please be aware that silicon carbide is a uh, high power required IC material. So if you are using a high power or designing or manufacturing a high power device, then you go with silicon carbide. So you want a medium and high frequency supportive device, then you go with the gallium nitride, like advanced mobiles, EV automotive chipsets, or what we can see, the low power consumption and high speed charging facilities like mobile chargers or any other gadgets that contribute in charging. So these two are advanced technologies, and this Epinovitech and Custom Dot are playing key role in bringing advancements and providing this GaN chips for all the companies who want to what we call the fabless companies, or even the fab companies. They want to start an IC or design an IC with GaN chip. So this intellectual property of GaN chip can be purchased from any of these vendors like Epinovatech and Custom Dot. So as I said before, these are the three trends that we have, and these are the three materials we have been using since 1970s to today, to date, 2023. We have silicon replaced by silicon carbide and gallium nitride. So if you want a high speed, go with the gallium nitride. If you want a high power, go with the silicon carbide. So you can see the examples of silicon carbide usage in practical applications used in railway networks, wind turbines, PV inverters. These are power related industries that use high power. So silicon carbide is doing that. And what you see is a high speed in GaN, wherein gallium nitride. Okay. So this gives an advanced uh, technology with a high speed, where you need a high speed computer, high speed mobile, uh, high speed automotive IC, okay, which has a very mass market compared to the silicon carbide or the silicon. So these are the advanced technologies, and GaN supports uh, high frequency at mid-range voltages. That means low power with high frequency, which is what we require in designing an IC, a best IC possible. So what we get out of this latest trends in the material, semiconductor material, is gallium nitride or gallium nitrogen that we see here, GaN, is faster, 20x faster in switching and 3x faster in smaller size and light speed, and up to 40% energy saving. And you have a higher power density of 3x, That means 3 times we have, and 3 times faster charging. So whenever you see a mobile phone coming up with a 45 watt or a 65 watt or a 66 watt or even 120 watts with a fast charging. So this is the technology behind, the material behind, used behind in creating that battery device or a chargeable device. So Navitas is one of the company that is working consistently on getting a better version of gallium nitride nitrogen IC, or a gallium nitride IC, because it has all these benefits of lower system cost of 20% compared to silicon, is very much required when you do a mass production or a high production or a high chip productions for automotive industry and mobiles. So the market for gallium nitride is very huge. So the current engineers, those are coming into market, what you see in the daily usage of mobile phones or laptops or a car or any device nowadays is mostly we are converted to gallium nitride. So all the design, all the ICs that you see today in the day-to-day life are basically designed using gallium nitride. So the market is huge because there are many applications of usage of gallium nitride. As you can see, starting with EV onboard chargers, DC converters, EV inverters, okay, sport cars, chipsets inside, okay, 5G base stations, the 5G network, solar microinverters, LEDs, advancement in different LED technologies, and servers, computer servers, CPU servers, mobile wireless phones, and wireless chargers, okay, smart homes, PCs, all types of computers, game stations, okay, and the final smartphones and tablet chargers. You have vast advantages compared to silicon, or even if you're just comparing with the silicon carbide, these benefits are enormous. So these are just the key to speed, efficiency, and size what GN provides. Coming out of Navitas is one of the manufacturing company who is working on gallium nitride. So these are all the customers that you have for gallium nitride, starting with Lenovo, Dell, MI, Nvidia, Oppo, LG Electronics, Xiaomi. These are just few that I have listed. You can take all manufacturers of portable chargers, wireless chargers to mobile manufacturers to laptop manufacturers. Everybody are going through this and using gallium nitride. So coming to the total overview of a long roadmap of trend that we have on the ICs from 1980s to the next 2040, from the basic personal computer driven by IBM and Intel to the latest SpaceX, the advanced research facility for space, uh, uh, aviation, and automotive, drones. Whatever you see today, all are possible because of advancements and innovations done by you, the engineers, the new engineers coming into the market, into the chip designing market. So you are making the change by creating innovations into the IC design and manufacturing. So as I said before, the companies like the foundries are the fabrication companies, those who have their own fabrication units. They can fabricate for anybody. Like what you see here, fabless companies come to the fab companies so to manufacture their ICs. So the end product might be any vendor who is a fabless product manufacturer coming into the fab, like TSMC, Samsung, Global Foundries, SMIC, UMC, AC, Amcor, JCT, SPIL. So all these are having their own fabrication units. So what you see in the NXP, Infineon, ST Microelectronics, Renesas, NVIDIA, Cypress, On Semiconductor, Texas Instruments, Xilinx, all has to depend on the fab, and they have to, end of the day, they have to use the other fab that you see in the left side to get their IC manufactured. So finally, once IC manufactured, these are the companies that use the ICs like Bosch, Panasonic, Harman, all these companies you see. And these are all vehicle OEMs that use these all ICs. Volkswagen, Ford, BMW, Audi, any bench, any automotive car that you see. So ICs everywhere. So this awareness is very much required. We'll discuss on what happens where lack of awareness. We'll discuss that also. So the challenges that we have in designing ICs and bringing them into market are, I have listed down to three important challenges that we have, and the geopolitical issues that we are facing in the current semiconductor industry. Let's see. One important and mainly affected is supply chain disruption. So supply chain disruption is something you are not able to finish the product, lack of a small IC that is very much required to finish the entire product. So there are multiple components or ICs on a single motherboard or a single SoC or a ASIC design, and a single component, if you are not able to get it, uh, lack of shortage of that particular IC due to pandemic and the Russia Ukraine war and the US and China trade issues, all these all contribute into chip shortage. So when you have chip shortage, you cannot finish a chain. I mean, chain in the sense the production of a full-fledged IC or a full-fledged motherboard, which will have multiple and small ICs. So the biggest affected and the highly affected uh, domains or sectors that you can see because of chip shortage are consumer electronics, automotive, and data centers. Okay, so there is a huge demand again for all of this. Consumer electronics is day-to-day usage electronics, and automotive is also day-to-day usage cars and vehicles that everybody is using in their daily lives. And data centers is, without data centers, no software company or any private company cannot work. They need data centers or servers. So this totally due to high demand and less chip production or a chip shortage will create limited manufacturing capacity and shortage of raw materials also because of trade issues. All this will contribute to delays in production. So currently in many automotive companies say that, for example, you have an issue with your car. In your car, a small IC is required. So when you go to the service center and ask for replacement of that particular small IC, he will just say that the IC is not available currently. We have a chip shortage. So that chip shortage comes when there is a trade issue or any pandemic issue. So production will be delayed, and they'll say check back in 3 months, 6 months, or some other time. Currently, we do not have that particular IC. So all this contribute to supply chain disruptions. And what the current companies can do or are already doing are ongoing with the current challenges is with the supply chain. They have to address this vulnerabilities because every company in this semiconductor industry contributes billions and trillions of money. So if a delay in production of that particular product, the competitor who has no trade issue or a pandemic, not affected with pandemic, comes into the market, which will create what we call less market for the existing top vendors. So there will be huge market disruptions where the new product vendor cannot come into market with the existing chip shortage of old ICs or heavily customer usaged ICs. So all these disruptions will are affected, and companies has to, or the industry has to look into this and diversify the supply chains to mitigate any further disruptions. So dependency is also a big challenge here, where you are dependent on a certain small IC to finish entire PCB or a motherboard. So the dependency has to be overcome by establishing strong manufacturing hubs and productions to be done at their own facilities instead of depending on a fab. So majority fabless companies have products and only few fabs are present worldwide. So that is also a biggest challenge. If a trade issue occurs, all fabless companies have to face this chip shortage. So next thing is technological complexity and miniaturization, where technology to use the standard material of semiconductor materials like silicon or like gallium nitride. So there are very few companies that are concentrating or creating innovation or R&D in bringing up this standard materials. So there are less semiconductor material providers in the market. So that is causing a lot of issues, and advancement in this technology also, the complexity, R&D takes a lot of time. So everybody is racing to reduce the size of their IC, the transistor size. So there is a huge demand with a hard time hitting the R&D and time to market and getting a quality product within the estimated time. So there are many issues that we have regarding technological complexities, and miniaturization is something where everybody is trying to reduce their IC size. The next important thing is the talent shortage, and the skills gap, what we see currently is, even though you have chip shortage or technology complexities, inversely affected by these resources. So if you do not have enough resources to help in chip production or designing or do innovations in the technology complexities, any advancements or innovations to be done, you need an engineer, you need a resource. So that is lacking. A talented engineer is very much needed in a chip design engineering or a chip designing manufacturing. So talent is very much lacking because of less people coming into the semiconductor domain. Even people who are graduated from EC background or electrical background, they are going into non-core domains like software or IT. So there is a biggest shortage of talent, and because of high demand of skilled professionals. So what are affected is the material science, device physics, process engineering, RTL design engineers, DFT engineers, physical design engineers, design verification engineers. These domains are highly affected and highly demanded worldwide with lack of talent and the skill. So obviously these are both contributing to hire an engineer. So first thing is how to train an engineer and bring up a good talent and cultivate the talent and improvise the skill has to be looked into by semiconductor industries. So semiconductor industries are already started investing in education. Even a basic service company is working on that to provide high quality education for what we call any research, for masters or PhD. They are contributing. So if you work for Wipro, HCL, whatever I have seen so far, any MNC company, if you see, they are providing investments or funding because you're already working in that company, or if you want to pursue that particular research course or a graduation, you can just approach all the MNCs into certain domains. So Wipro has that, I have seen, HCL has it, Cient has it. Any company that you name that is MNC has all these investment options. And product companies like Intel, Broadcom, Xilinx, Cadence, AMD, Nvidia, they have it since long. For the 20 to 25 years backdrop, they have this investment of money or funding into the education of existing employees or new trainees. So that is one thing that has to be done. And mentorship, internship, apprenticeship, all this also has to be looked into by the industry, and they have to hire fresh graduates and train them and bring up the talent and fill the gap of the skill set. So there is a huge opportunity that is required. They have to collaborate with the institutions and like training institutions or the academic educational institutions to provide these courses part of the graduation or post graduation, so they can come out ready to work in the semiconductor industry. So what are the career growths and the future scopes that we have with a little bit of what we call the gaps in the career growth in the semiconductor is that lack of awareness. So the current educational institutions who are providing the graduation or post graduation are not technically providing the advanced or the industry standard learning courses within their curriculum. So what we have in the current market is certain institutions who are only training the industry standard courses are helping or contributing in filling the gap of talent shortage and skill set engineers. So these engineers has to take up any quick start programs provided by the MNC companies or a training institutions, which will train you in a VLSA training programs and help you become semiconductor ready. So you become you will be easily hired with the completion of these courses. So the biggest disadvantage compared to the software in the chip design industry is that you have to go through the industry standard tools experience and the course mandatory to enter into chip designing. Unlike software, users learn the programming language, the software programming language, and enter into software. But in this domain, it's not possible just by learning the Verilog or VHDL coding or the RTL language required for chip designing. You have to go through a proper industry standard training, because in industry the tools that we use are highly priced and only available in the MNC companies, and those who are providing trainings like training institutions, they have these advanced EDA tools which are practically used in the industry, so which are not again used in the academic institutions. Like in colleges, no one will purchase a 1 crore or a 2 crore valued EDA tools for their academics, because you do not have the advanced course of industry standard courses in your curriculum. So the advanced tools are also not required. So they don't buy it, they don't have it. Only the NITs, IITs, triple IITs, the biggest institutions who are providing the skillful resources directly placed in the MNCs after their graduation. Only they are contributing and providing these advanced courses part of their curriculum. So those are not coming out of these top institutes, educational institutes, has to definitely go through the industry standard tool training and a course to enter into chip designing. And it's a one-time learning, unlike software. This is an advantage in chip designing, where you don't need to learn new language every time, every year, or a change of technology in software every time. You need to upgrade. There is no such thing in chip design. The basics are the same combinational logic design concepts that you learn in your academics, coming from the core domain. So nothing changes. Basics are the fundamentals, and fundamentals are being practically utilized and used. Nothing else. There is no upgrading of fundamentals, only the advancement of the fundamentals that you practically learn when you start working as an engineer in the chip designing. So, as I said, the current education institutes also have to take up this apprenticeship, internship programs, and add this industry standard courses into their curriculum. So what we see here is many universities, like there are close to 20 universities in AP, Andhra Pradesh, Telangana, and Karnataka, which are contributing contributing to this talent shortage. They are trying to bring a huge number of talent resources into the market by taking the fresh graduates uh, and sending them through internships and apprenticeship to this semiconductor companies. So Micron is recently has done that. So this is the latest. So I have noted it down here. But there are many companies like Intel, AMD, and Wipro, HCL hiring from directly from the colleges, or hiring the trained freshers from the training institutions like Successbridge or any other training institute that you have in the market. So you have a biggest scope because you have challenges that are creating huge demand for the uh, fresh engineers or the graduates coming into chip designing. So the demand for engineer is a big challenge to the semiconductor industry. Only through the training institutions or educational institutions, by adopting this industry standard programs, we can achieve that. So there is a huge demand, and there is a huge career growth within this semiconductor. What we see since 2012, I have been seeing uh, the spike of demand in semiconductor has never let down. It's always to the top. So current companies that we see in India, the top semiconductor stocks in India, are this Moship is one of the appreciable and highly skilled resource company situated in Hyderabad in Telangana state. So I have seen this company for many years, starting with a group of skilled engineers. They have started this company. Now it has grown to a stage where it is registered in stocks, and it is providing huge contribution to semiconductors coming from made in India uh, and make in India concept provided by the current Prime Minister. Uh, so what we have here is ASM Technologies, SPM, Rutansha, Tata ELXC, and Dixon. These are highly contributing, and these are registered in the top semiconductor stocks in India and addressed by Narendra Modi, the Prime Minister. So few things that we're seeing here is and need to be addressed is India has never been a semiconductor hub for manufacturing. It has only been the resource provider so far. So as we have these many resources going and working in states and the other countries, um, why don't we have our own fab, which has created this Make in India concept by our current Prime Minister Narendra Modi. So the Make in India is making a difference comparative to all other countries in the semiconductor market. So in 2021, the Central Cabinet has taken a decision in creating our own manufacturing fabrication units within India. So we do not have fabrication units till 2021 in India. Now we have a lot of fabrication units coming into India, invested by the foreign investors, and including the in-house, the top Tata is investing. Tata is investing, the Micron, Intel. There are many companies, those who are not originally from the India, are also foreign investments are very high, and internal Indian investments are also going to be very high in this silicon semiconductor fabrication units, increasing the production and creating a trend in the market. So what they have decided in the cabinet decision for the semiconductor is to have silicon semiconductor fabs, display labs, and compound semiconductor silicon photonics sensor fabs, and packaging, semiconductor packaging and design. So all the upcoming engineers coming from core industry, or even from the non-core industry also, can enter into the semiconductor by just learning the proper industry tool training and the course. So semiconductor design will have more requirement, because designing is a primary requirement of manufacturing or creating any IC. So these are also a part of the scheme, Make in India scheme, where we will be supporting up to 50% of the project cost if we are starting any semiconductor or setting up semiconductor or display fabs within India. So this government, the Narendra Modi, has promised and amended this Make in India scheme, where he will be supporting up to 50% of the project cost. So that's a what we call biggest help that any government can do. I have seen all the countries in the world contributing to in-house or making in-house fabrication units. Even USA, they have never contributed to support 50% of the project cost. I have never seen that. This is the first and only country that is providing the support to the semiconductor fabrications. So we also have a support of 30% of capital expenditure if you are setting up compound semiconductor silicon fabs and packaging facilities. So anybody is trying to set up or interested in setting up semiconductor fab for packaging and silicon material like silicon and GaN, the compound semiconductors, and government is going to support up to 30%. That's a huge investment or a support, really appreciable for the government. Design linked incentive is a scheme where if you are eligible, any startup, like training, starting from any training institute also, okay, any training institute can go and approach the government website and check for the eligibility. And if you are starting any training institute or any institution that is supporting new engineers, semiconductor trained freshers or engineers into the market, then this DLA scheme will give you up to 50% of the setting of the expenditure involved in the creation of these institutions. So DLA is very helpful for the upcoming institutions. And product development linked incentive on a net sale for 5 years. So incentive is provided if you're bringing up the product into the market for the next 5 years. Incentives are provided by ratio of 6% to the 4%. So that is also a big support. On top of all the support from 50%, 30%, and this DLS schemes, even the product development coming into market, once the IC is coming into market, then he's getting an incentive. That is also a big support. So what you can see here is the career growth and the future scope of semiconductor coming into semiconductor. All these are contributing because Make in India will create new resources and huge demand for the engineers. So this is what you see. Make in India will contribute US 1 trillion digital economy as part of US 5 trillion GDP by 2025 to 2026, and production target worth 9.57 lakh crores over the next 20 years. Exports are expected to touch 5.515 lakh crore over the next 20 years. So all ICs will be exported to other countries from India in these next 20 years. What we see, once the fabrications are situated, the units are situated in the next 2 years, then we can see a good growth for the India and the engineers, the passed out of many engineering colleges. So we have ISM, who is contributing to validate. There is a bench of people like the top MNC companies who are contributing to Make in India. So they have there is a panel the government has finalized, and their vision is to implement this Make in India concept and look after this roadmap. So there is 300 billion, 18.75 lakh crore in the next 2 to 3 years. So there's a biggest future scope for any engineer entering into semiconductors. Yeah, so that's it from my end. Thank you everyone, for all the participants and audience for patiently listening to the seminar.
Thank you, Mr. Ganesh. It was really very useful, I think, for all of us. So maybe we can take a few questions from the audience, if there are.
Yes, definitely. Any questions from the audience?
Yes, I have one question.
Yes.
So I just wanted to ask or understand, like we understand that government is just going to invest 3 billion in the semiconductor industry, but if we see the other countries like Finland, UK, or Germany, so they're basically they're going to invest 300 billion. So with this amount, will the industries will be able to pull the good resources inside the companies? So how it's going to help?
So actually, we are talking about Make in India, and within India, creation of new fabrication and creating new ICs coming out of India and entering into the market. So India already has enough resources because we are the highest resource producers of semiconductor engineers in the world so far. So we have already many engineers who are going into other countries because we do not have our own fabs situated in India so far. So we already have the resources. The funding is only required for manufacturing.
Will they move back to India? Will they move back to India if during this initiative?
So I have seen many engineers are already moving back to India. So once the economy is stable, once the manufacturing industries are established and huge investments coming into manufacturing semiconductor, obviously you will have huge packages. Already the current packages in India are competing with the other countries, apart from the conversion of the currency. You can see China, Japan, Taiwan, Malaysia. Indian salaries, Indian semiconductor engineer salaries are far equivalent to these countries. Or I can say in Malaysia, if you see, at least for comparing to Malaysia, I would say the salaries given to the engineers in Malaysia are very less compared to what we get in India. So the lifestyles are different. The people are getting adapted to other countries that is the only lacking within India. Otherwise, we have huge salaries provided to the engineers. So I hope so.
Yeah, but for this industry, every country is trying to pull this. I mean, because there is a huge shortage of the chips in the world. Correct. Because everyone is going. Going digital. So because of IoT. So if you see like those who are even renting their houses through Airbnb, they are just using the IoT keys to unlock it remotely. So we see electronics everywhere. So that's why the whole country, even the Western countries and developed countries, are trying very hard to pull the resources. VLSI engineers mostly. Right. So it will be easy for us, like if someone has been offered by US or Germany with a very high package, it will be so easy for Indian companies as well to pull them back.
I have a good answer for this. So the same wise, India has never said that make in India and we encourage only Indians to work in India. There is no such concept. But if you see the new trends across the world, US or any other countries, they are trying to do make in their own country, as well as the first priorities to their own country people, always, particularly US, China, Japan, because of the they don't want to share the intellectual properties or the designs they have come up with, the innovations. So this is there with every country, and every country is lacking the resource where Indians are being hired in their countries. So this will slowly drop, because I have seen, and I'm still seeing that today in 2023, only few companies are hiring the external resources and underpaid compared to what we can get with the cost of living that we have in India. So that is a big advantage, because India has no trade issues with any of the countries so far. But US and Russia, China, these are the big players throughout the world, which has a huge rivalry or issues with the trade because of the power conflict or everybody is except India, all the countries are power players. Everybody want to become the top country or the powerful country in the world. So we do not have that competition. If we become our self-sufficient and having huge population and a huge number of inside resources or the fresh graduates coming into every year within India, I think this Make in India will make a big impact and we will be successful. From my experience, I see that in that angle, because I'm in Malaysia currently working, and I have seen companies and I am roaming across, working and tying up with the industries. So this chip shortage or in-house making policies of every country, they don't want to encourage other country people to come and work on their own in-house, because the trade secrets and intellectual properties are a big concern, particularly for China, Japan, Taiwan, US and Russia. They never encourage. So one or two engineers or hardly you can count 1,000 engineers going out of India, and lakhs of engineers existing within India will make a big impact. Yeah.
Thank you.
Thank you. Thank you for the question. That was a valid and good question. I hope I answered.
Any further questions? So, Professor Dr. Zahir Hassan sir, do you have any questions?
Yes.
Yep. You can please ask the question directly.
Basically, I am interested to know regarding the research area for the mechanical engineers and electronic engineer in the field of semiconductor.
Yes. As you can see, there is a requirement in the semiconductor fabrication where you have to work with what we call the machines, the testing devices, AT testers, and everything in the semiconductor fab is automated. Everything is a machine. So mechanical engineers have the biggest benefit here, and electronics are by default part of the semiconductor, but mechanical engineers being mechanical engineers, it's a biggest benefit for them if they enter into this semiconductor industry, because everything is a mission. Even we design engineers, I have worked so far as a DFT engineer. So I use 80% of the tool and only 20% is my work. So rest of the thing is done by the EDA tool. And end of the day, once it gets to manufacturing, everything is automated. Yeah, automated in the sense you have a perfect machine to create an IC once the design is given to the IC. So we are just signing off the design to the machine and machine will create that IC. So mechanical engineers are required in this handling and maintaining the equipments and machines in the semiconductor fabs. So that will be a big advantage. So electronics are by default. Even the diploma engineers are, if you see any fabs, the basic engineer you will see is the diploma. So those who have done their diploma also, they can directly enter mechanical or electronics or electrical. They are easily accessible and can enter into the semiconductor because all fabs require these engineers. And recently I have seen civil engineers are also required because new fabrications units are coming into the each and every country. So you are being hired to until this fab is manufactured, the fab is established. So in order to do that, you need civil engineer also, and you need mechanical engineers. So I have seen even in Taiwan, Malaysia, Japan, and China, many of the Indian resources are being hired. So there is no differentiation between these engineering groups. All engineers have equal share and benefit, but being electronics engineer has a more share because you need a design engineer end of that. So the benefits are the same for all the engineers.
Okay, okay, thank you.
Any questions? Any other question? Okay, seems like you can wrap it up. If there are no
Any
questions.
last questions from the audience before we wind up the session? So I think there are no more questions. So I would like to thank again all the audience for attending the webinar, and especially Mr. Ganesh Kumar, who took out his time from his busy schedule and imparted lots of information to us. It's an exciting field, and maybe we can hear more from Mr. Ganesh Kumar whenever he has some time available for us.
Sure.
So with this, we can close the session for today. So thanks a lot to all of you. With this, we close the session.
Thank you. Thank you, everyone. Have a good day.